Hi everyone. In this lecture, I'll try and present a very brief history of MOSFETs. So to begin, I'll start with the first discovery of an amplifier which happened around early 1900s. So which is around 1907 to 1910. So that's when the first vacuum tube amplifier was invented by DeForest. From vacuum tube amplifiers nearly ruled for 4 decades until in 1950s we shifted to bipolar junction transistors. And in 1950s and 60s we had bipolar junction transistors and its distant cousin. It's also a junction transistor, but it's called field effect transistor or junction field effect transistor, JFETs. And eventually to the recent times, MOSFETs completely replaced bipolar junction transistors in most of the applications. Bipolar junction transistors are used in some very rare, or rather in extremely high frequency applications, or in some very niche applications like very high precision, or rather very high voltage gain amplifiers. But generally, most of the digital and analog and RF integrated circuits today are implemented using MOS technology. So to briefly understand amplifiers, so any amplifier, all these amplifying devices, be it a vacuum tube amplifier, a bipolar junction transistor amplifier, or a MOS amplifier, or a junction field effect transistor amplifier, they operate on one simple principle. So all these devices are 3-terminal devices. The current flow between the 2 terminals, so for example shown here is a vacuum tube amplifier. The flow of electrons or current between the 2 terminals is controlled by a 3rd terminal. Then if we can attain a device, if we can build a device wherein the flow of electrons between these 2 terminals can be controlled by application of voltage at the 3rd terminal, then we have an amplifier. Now, provided this amplifying device should also satisfy the simple condition that the terminal at which we are driving the input should draw very little to no current. If that condition is satisfied, then we can attain huge power gain. So which means there is some finite current that's flowing between the output terminals, and when you connect a load or a load resistor, you will be delivering a finite power to the load. And if you are not going to draw any current from the gate, from the input or the control terminal, which means you are taking in no power but you are giving out power to a load. So which means there is a huge power gain. So that's the fundamental principle behind all these amplifying devices. All of them are generally 3-terminal devices. You try to control the flow of electrons between 2 terminals by the application of voltage to the 3rd terminal. So around 1907 to 1910, around 1907, 1908, the first vacuum tube amplifier was invented by Lee DeForest. From then, these vacuum tube amplifiers were used for telephone communications. And first it was used in radio communications, in building radios. That was one of the most popular applications of vacuum tube amplifiers. Then later on they were used in World War, they were used in telephone communications. The long distance telephone communications was made possible because of vacuum tube amplifiers. And vacuum tube amplifiers were also used in the first generation computers which were used during World War II. So shown here is a picture of a radio, a vacuum tube amplifier, a radio built using vacuum tube amplifiers. The vacuum tube amplifiers can be seen inside this, the radio that's built using a vacuum tube amplifiers. Now one problem that engineers faced with vacuum tube amplifiers is that the fundamental principle in which vacuum tube amplifier operates is on thermionic emission. So first you have a terminal which it's called cathode. You generate electrons on that terminal by heating that terminal. So a separate coil is used, a huge voltage is applied to this coil, and that coil is heated, and the heating is like an I2R heat, I2R losses based heat. So when you heat this coil, it's going to generate or emit electrons by this process of thermionic emission. Now these electrons will then be drawn towards the anode or the positive plate. So we will ensure that the voltage here is greater than the cathode voltage. Then the electrons will be attracted to the anode. Now the flow of electrons can be controlled on a third terminal called the grid terminal by applying an appropriate voltage. So by doing so, an amplification operation is attained, and this led to a long distance telephone communications, and even radio sets could all be practically built using this vacuum tube amplifier. But the major problem with this device was that you need to heat this coil, and that required a lot of power, and the devices were also bulky. We had to create vacuum, and so those devices were naturally bulky. So that was one major problem, and therefore naturally we needed a better amplifier which is compact in size and also consumed much lesser power than this. The answer to that was a bipolar junction transistor. But the invention of bipolar junction transistor didn't come off directly up from vacuum tube amplifiers. Let me take a small detour and show this. This is a picture of a bipolar junction transistor based radio, and you can see this the inside view of the bipolar junction transistor radio, and one can immediately see that the size of the transistors here, so these are actually a combination of both JFETs and BJTs, and so here you can see the amplifier that's shown here is JFETs. They are much smaller in size as compared to the vacuum tube based amplifiers, and also they consume much lesser power. In fact, the bipolar junction transistor was actually introduced or invented around late 1940s and early 1950s. By then, vacuum tube amplifiers had been used for nearly 4 decades, and when bipolar junction transistors were made practically available, it was a significant shift in the design of circuits, or in the direction of amplification, because that was a huge reduction in power. The power was reduced by several orders of magnitude. So that's why the shift of amplifying devices from a vacuum tube amplifier to a bipolar junction transistor based amplifier was a welcome shift. It reduced the area, the devices were more compact. The power consumption, because there was no heating necessary, so the power consumption reduced significantly. And that was, it was compact, and also power consumption reduced by several orders of magnitude. And therefore, bipolar junction transistor was the best answer or the best replacement for vacuum tube amplifier. So that's why we switched to bipolar junction transistors. Now, but the idea of the shift from bipolar junctions to MOSFET is not something as obvious as the shift from vacuum tube amplifiers to BJTs. Because a bipolar junction transistor, we will see when we compare BJT and MOSFET, is a superior device as far as its analog performance is concerned. Meaning bipolar junction transistors can operate at higher frequencies than MOSFETs. They also give, for a given current, bipolar junction transistors end up giving a higher transconductance than MOS amplifiers. But the invention of bipolar junction transistor actually began with the idea of a MOSFET. In 1920s, there was an idea to build a field effect transistor device. So wherein we have a semiconductor material, and we bring a metal plate closer to it and apply a positive voltage to it, and this will draw electrons closer to the surface. The electrons present in the bulk of the semiconductor will move closer to the surface, and then by applying a voltage between these two terminals, we could actually modulate the surface resistance between these 2 points. So as we discussed, if we can modulate the resistance or the flow of electrons between 2 other points by the control of a third terminal, then we attain an amplification operation. So we explained how do we attain this amplification operation by the control of a third terminal. So what essentially we are doing here is that we are trying to build a dependent current source. So between these 2 terminals, we are able to generate a current, and that current is not dependent on these 2 voltages, but rather it depends on a voltage at the third terminal. So we are essentially building a dependent current source, and if I can inject that dependent current source, the current generated from the dependent current source, into a load resistance, And by choosing an appropriate value of the load resistance and the value of the dependent current, then I can get amplification out of it. So I had already discussed this in the first lectures. How should the IV characteristics of such a device look like? And we said that if we can, any amplifying device, if any device exhibits an IV characteristic, which we will discuss at a later stage, IV characteristic that looks like this, wherein the current that's flowing in the device should be independent of the terminal voltage, the output terminal voltage, but the current should depend upon some external or the third terminal. So then it's a dependent current source. If you can build a device with these IV characteristics, then this device can be used as an amplifier. So that's what we discussed in the initial lectures, and we showed how a bipolar junction transistor can be used as an amplifier. Now I'll come back to this point. So this was in around 1920s. The idea of building such a device was being considered. Now this task was taken up by William Shockley at Bell Labs, and a team of engineers, Budin and Brattin, started working on this, and they chanced upon the first transistor model, the first transistor which was built after a vacuum tube, a practical amplifying device that was built after a vacuum tube amplifier. That's the point contact transistor, which is shown here. So this was the first device that was actually built, which a working device. The problem with this field effect device was that the surface, with the electrons which drifted to the surface, the phenomenon was not well understood, and they could never build a practical device that could be used as an amplifier. So even though the idea existed, there was a problem of building this device practically. So in the process of the engineers in Bell Labs started with building a field effect device, but eventually they landed up in a point contact transistor. From point contact transistor, this was around 1947-48, William Shockley thought of the idea of a junction transistor, which eventually is your bipolar junction transistor. So this was in late 1940s and early 1950s. Since it's a junction based transistor, a similar device was also invented around the same time in 1950s, and that was your junction field effect transistor. So as I said, in all these devices, junction JFETs, BJTs, we try to control the flow of current between two terminals as shown in this figure by the application of a voltage at the third terminal, and mostly by the application of voltage at a third terminal, and mostly the third terminal draws little to no current from the input. So then if we can build a device like that, then we can attain power gain. So that's then, if such a device will be an amplifying device. So then after that, in 1950s, late 1950s and 60s, a new device was built, going back to the same idea of the field effect device, and that device was your MOSFET. So in the MOSFET, in between the semiconductor and the metal gate, the new idea was to introduce silicon dioxide, and that resolved the problems that they were facing previously. So this silicon dioxide, once the silicon dioxide was introduced, then this structure came to be known as the metal oxide semiconductor structure, or MOSFET. It's a metal oxide semiconductor, and it's a field effect based device. So metal oxide semiconductor field effect transistor. So it came to be known as MOSFET. So this is a very brief history. We have not gone in depth, but a very brief history of the invention of MOSFET. The next lecture, I will discuss about the physics of the current conduction in MOSFETs.